Hey Logic students, this is your Professor O'Million, Chuck, and today I want to bring you through or guide you through a practice set on how to detect semantic properties with truth tables. Right, so I've gone over this a little bit about how we do detect semantic properties with truth tables, but I want to actually have you do some of the work, while I'm actually kind of lecturing in this video, which is weird. I understand that, but it's not something we've done in depth a lot here, but I think it might help because there's going to be a number of questions on the midterm exam and then also on homework 5, and I just kind of want to show you how to answer them. And I also want you to learn a couple things along the way, to some shortcuts and some theorems about logic that you should be aware of. All right, so you're going to encounter a question that kind of looks like this. Right, you'll have a question that says something like, for each pair of formulas below, make a truth table to indicate whether the first logically entails the second, whether they are logically equivalent, or whether they are logically consistent or inconsistent. Okay, so now in this case, you have to understand more than one property can apply. All right, so we want to take a look at this. When it says the first logically entails the second, what we want to do is just kind of look at what we got here. All right, notice that you have two formulas here inside some brackets in a set, so it's like a set of formulas, right? And they're separated by a comma. And so the first one is going to be the biconditional, and we're going to determine whether or not it entails this one, which is a conditional. Okay, so I want to give you a step-by-step procedure on just how to do this, right, in a kind of a comprehensive way. You'll probably memorize this quickly, right? But it is something I'll just want to, it'll help kind of guide your steps at first here. Right, so first thing you do is determine the number of distinct atomic subformulas that you have in the well-formed formulas that are given to you, and then count them up and call that number n. So in our case, right, all we had was FA and GA, right? So if you look back here at the two formulas, it's just FA and GA that are showing up. Right, so then the second thing you got to do then is then construct a table with each of the atomic subformulas at the head of a column on the left and in alphabetical order. And the well-formed formula is under review at the head of a column on the right. Okay, so the table should have 2 to the n rows, where n is the number of atomic formulas that we have. And so in our case, we have 2, excluding the head of each column. Right, and then under the subformulas, write down every possible combination of truth values. Right, so all that kind of sounds a little abstract. So here's what concretely it looks like at the end. Right, so you parcel it, you find out, okay, these are the 2 atomic subformulas, you put them in alphabetical order. Right, then you come up, okay, that's going to be 4 different rows, and then TF, 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 right, and then TT, FF, and then you're done. Okay, and then you got the 2 formulas here, they're given their own column. Now, the way I've kind of set things up here is that I wanted to, I wanted to isolate each little individual component of this one. This one I kind of know already a little bit. It's biconditional. Okay, that's pretty easy. But this is a little more complicated. This has a negation in it. It has an or symbol, right? And then you have a consequent of a conditional. So I kind of broke things up a little bit more, at least in my my PowerPoint lecture here. All right, so those are the first 3 steps. That's what it's going to look like. Right. The 4th step then is to use the left side's truth values to evaluate the truth value of every atomic subformula in your problem. Okay, and then invert any truth values, 1 per row, of course, under the negation operator of the subformula. Okay. Now what that's saying is pretty simple. All right. It sounds more complex than it is. Right. But if it helps, you just take the information that you have over here and you put it under the relevant atomic formulas as they show up. Right, this one I kind of know already, so I'm not going to worry about that one. But this one I don't. This is, the main connective here is a conditional, so I really want to know what my antecedent is saying. All right, so what I'm going to do then is then just plug those in where they go. Right, and I want the F formula in there too because this is part of a disjunction. And I have a negation here, so I want to take the information from the G column and just invert it like so. So now it says FT, FT, right? Okay, so got that part done, and then we're just going to determine, right, the truth values of any remaining subformulas and work our way to the main connective. All right, so that's basically what we're going to do, and repeat that step until necessary, until we get to the main connective. right? So I'm not to the main connective yet of this conditional. I need to figure out what the consequent says, and the consequent is a disjunction, and disjunctions are false if and only if both sides of the disjunction are false. So row 3 is where I'm going to mark my falsehood, and then in every other case I see that it's true, all right? Because they're true if at least one side is true, and so that's what's happening. And so I mark them true. Okay, now I'm ready to solve for the main connective of the conditional, all right? And so I know that these things are false if and only if you have a true antecedent and a false consequent. So in row 3 is the one case where that happens. In every other case, it all works out. It ends up being true. So that part is done. Now, like I said, I told you I know how this works. Even though this is not in alphabetical order, it's saying GA double arrow FA, I do know that if both sides of the biconditional are true and both sides are false, then it's going to be true, and then it's going to be false if they mismatch. And so I'm going to get the familiar pattern TFFT, right? So now everything is all done. The truth table is correctly filled out, and so now I can start answering the questions that I was asked by the problem. So the first question I need to answer is whether the first logically entails the second. All right, so does the biconditional entail the conditional? Okay, and I use a little double turnstile there to kind of indicate entailment. And the way I detect that is to go back to my cheat sheet and see, okay, now is there a row? Okay, is there a row where there's a T under the main connective for the conditional, but a false under the main connective for the or I'm sorry, I said that wrong. A T under the main connective for the biconditional, and a F under the main connective of the conditional. Okay, because that's what P and Q are talking about in my problem. So I find the rows where the biconditional is true, and it's right here. And then I look over at the conditional, and hey, guess what? They're both true as well. I'm never moving from a truth to a falsehood, right? I'm never moving from a truth to a falsehood, so entailment holds. Okay, so now that's good. Now you might be wondering, well, what about going from a false to a false or a false to a true? Doesn't that destroy entailment? And the answer is no. Remember, falsehoods kind of don't really matter in the analysis, right? We want to talk about truth to falsehood. And if that doesn't happen, then entailment holds, right? So the question, what about falsehoods, right, receives my reply, well, what about them? They can go F themselves, right? My little dumb little joke, right? I hope that's memorable. And so, that can help you not get confused when you're testing for entailment. All right, next question. Are they logically equivalent? All right, so remember, equivalence just means, okay, so is the biconditional equivalent with the conditional, right? And so if that's the case, in the truth table then, both of those then should have the same truth value under their main connective in each row, okay? But they don't. If you go back to the truth table here, you'll see in row 2, one of them is false, right? The biconditional is false, and the conditional is true, so there's no equivalence, all right? Now, there is equivalence in the first row, in the third row, in the fourth row, but since you have this problem in the second row, there's no equivalence, all right? All right, so then for each pair, now we need to determine whether or not they are consistent or inconsistent, right? So if you go back to our little cheat sheet here, all that means is that we got to figure out if there's a row where the conditional and the biconditional are both true together. And they are, right? So row 1 is a great example of that. That's all I need for consistency. All right, now it also occurs in row 4, so we have kind of a wealth of options to choose from here. But that's all I need. All I need is one row where they're both true. Okay, so the answer to the question then is that the first logically entails the second, but they're not logically equivalent, and they are logically consistent. All right, so there's more than one answer there, right? They are consistent, and entailment holds between the first and second, right? Okay, so that is basically the lesson for today on how to do that stuff. But it's not where the video is going to end, because what I'm going to do is apply that method of kind of determining how to, what semantic properties some formulas have with truth table. We're actually going to do a bunch of those kind of problems. We're going to go through 10 of them, right? So I am going to go through them kind of quickly, right? But I'm going to tell you to hit a pause button and try to work it out yourself, right? And then come back and then see how things look, and then I'll kind of explain what's up. All right, so that's going to be what we're going for, what we're going to do going forward. All right, and so here we have the first problem. This says to use a single truth table to show that this conjunction here entails well, what is this thing, right? What does that mean? let's go, well, you know, our little cheat sheet will tell us. Remember, whenever you kind of see P entails upside down T, right, what that means is that the thing is a logical falsehood. So when you're trying to show that it's logically false with your truth table, you're going to try and find an F under the main connective in every single row. So an F under that ampersand. So, you know, take a minute, couple minutes, you know, work that out and prove that, and then come back, restart the video, right? Just hit the pause button, and we'll go over it. All right, so this is something that you should have come up with. All right, this is what it looks like. All right, now I fill in everything, you know, using the little truth table program that I was using here. So it looks kind of like overkill, right? But that is what we're doing, right? In that main connective there, you see it's false in every single row. Okay, it's false in every single row. And the two columns that you're comparing, right, are the two biconditional connectives. That's what you're comparing, okay? All right. Now, we're going to prove the following theorem. Is, you know, I'm sorry, here's the theorem, okay? If a formula is logically false and Q is any arbitrary formula that you pick, well then the formula P, right, that we were talking about entails Q. So if P is a logical falsity and Q is an arbitrary formula that you pick, then P entails Q. Now we already got a logical falsehood that we just used, so we can use this one again, all right? And then we'll just pick some random formula, right? You could pick like not GA or something like that. That might be one, or not GB, okay? Or so, you know, that would be okay. All right, and so if you do that, then what you want to do then is show there's not going to be any row where there's going to be a true under the conjunction here because it's logically false, and you're never going to move from a truth to a falsehood, right, under the whatever arbitrary formula you pick. Now, I'll give you a minute to do that, so just hit the pause button, and we'll come back. Okay, so this is the formula that I picked. I picked K. All right, now I probably should have put not GA, because then at least, right, I would have only had 4 rows I had to display, but then once I added K, I had to do 4 more, so I have this 8-row truth table. But notice how I'm never moving from a truth to a falsehood here. That's because the pattern of true to false is not going to occur when you have a logical falsehood in the mix. All right. Logical falsehoods entail everything. This is actually a useful piece of information. This is not just a piece of busy work. We'll be making use of this idea when we get to derivations. It's actually very, very handy, and so it's not something I just take you through for the sake of busy work, right? But logical falsehoods, they entail everything. That is the case, all right? All right. So question 3. Here what we're going to do is we're going to see whether or not entailment holds, right, between a conclusion of an argument and the argument's premises. So treat these things, whenever you kind of see a set of formulas separated by a comma, treat those as premises, and this is a conclusion. So what we're going to do is determine whether or not there's logical entailment. Now, what we need to do is show that there's no row where there's going to be a T under the main connective for both of these, right, the conditional and the atomic, all right? So we got to take account of 2 things here, right? And then, you know, if there is 2 truths here and then a falsehood, then there's going to be no entailment, all right? But if there's no row where you have 2 truths and a falsehood, then entailment holds, okay? So work that out. Work out that truth table, all right? And then hit the pause button, come back, and we'll talk about it. Okay, so you should have come up with something like this, all right? Here's the main connective in blue there under FA arrow GA, right? And then there's FA, right, which we have here too, I understand. Okay, but notice here, the row 1 is the only row where you have 2 of them being true. So that's the one you have to worry about. And so if you have an F and a T and a T and an F and a T, you know, you don't have to pay attention to those, right? What you need to have are rows where the premises are consistent. Okay, then you check your conclusion, right? And so you see, right, that it's true. And so there's no row where you have 2 truths and a falsehood. Okay, so entailment holds. Okay, using a single truth table, what we want to do here is show that, well, what's going on with this now? We have turnstile and then formula, right? Well, if you remember from the cheat sheet, when you see turnstile formula, what that's saying is that the formula is logically true. Okay, so we want to see a t under the main connective here, which is this conditional arrow. All right, we want to see that. So prove that with the truth table, work on that, and then come back. All right, so this is what you should have got. Okay, you should have gotten a row of t's under the main connective. Now, you might have noticed here, like, well, this is a double negative. Did I really have to fill it in? And you know what? The answer is no. I mean, you don't really have to, okay? In this case, it's pretty obvious. Now, maybe in other cases it won't be, right? But you should, right, at least pay attention to that, okay? And then, you know, just figure out, right, you're going to compare this column with this column here. And you'll notice that this is going to come out true in every case, all right? All right. All right, so that's how that works. All right, now, question number 5, right, is going to make use of what we learned in question 4. And what we're going to do is prove that an argument is valid if it has a logically true conclusion. Okay? All right, just hold on a second here. All right. Okay, had to cough a little bit there. That was no fun. All right, but anyway, so let's talk about this. All right, we want to prove an argument is valid if it has a logically true conclusion. To do this, you can use a logical truth. So like the one we just proved in number 4, or another one like P arrow P, right? So just, you know, pick something like FA arrow FA. Then pick any set of well-formed formulas for premises that you like. And remember, a set can have a single member, right? That's actually okay in set theory. Okay, so what you're going to do then, right, is we're going to try and show that entailment holds, right, between any formula that you pick and the logical truth that we just proved. And so work on that, do that, and then come back and we'll talk about it. All right, so what I did is I picked K again. K is going to be my premise. And so that, you know, now I have to do 8 rows of this, okay? But now notice this, though, all right, is that I never go from a truth to a falsehood, right? K, whenever it's true, so is my logical truth. And of course, the logical truth has to be true because it's true in every row. So you never move from a truth to a falsehood. So this proves another theorem in logic, is that logical truths are entailed by everything. All right, so logical falsehoods entail everything, and logical truths are entailed by everything. All right, so just a little fun fact for you to remember. All right, and okay, number 6, what we're going to do now is determine whether or not this formula here is logically true, logically false, or logically contingent. So here, there's not going to be more than one answer. There's only going to be just one answer. And we know what logical true means in a truth table. That means that there's a true under every row, under the main connective of every row. Logical falsehood means there's a false under the connective of every row. But contingency is different. Remember, contingency, what that means is that you have a true under the main connective in at least one row, and a falsehood under the main connective in at least one row. Right? So work on that and figure out whether or not the formula is connected, is one of these properties. All right? All right. Okay, so you should have gotten logically contingent, all right? And the main connective here, if you were thinking it was this disjunction, that was wrong, okay? If you thought it was this biconditional, that was wrong, right? It's actually this negation. It's the outer, you know, look, it's on the outside. So those negations, you gotta watch out for them, right? They are pretty tricky. And notice that it is contingent because if you were solving this and figuring out, you would have seen on the second row, filling out the main connective here, is that you would have gotten a T and an F. And that right there shows that it's contingent, okay? And so you can actually stop your work at that point and just mark your answer because that's all you need. That's all you need to show, all right? Okay, question 7. Your job here is to determine whether or not these premises, all right, entail this thing. Okay, so this is a lot. This is a lot to keep track of here. So here's the first one you got to keep track of. That's a formula. That's a disjunction, by the way. And then you have this thing, right? That's a biconditional. And then here you have a disjunction. So you got to figure out, right, whether or not entailment holds. All right. So what ends up happening here is that if you can find a row, right, where these are true and this is not, then entailment won't hold. All right, so work on that a bit. All right, so I don't know how far you got in this, but you should have found that it does not hold, right? And okay, let me just pause for a moment and fix this here. I'm not sure what happened, and let me pull this up here. All right, we're back. Okay, now things are in line. All right, so while this does look like a lot of work here, if you just look at this very first row and kind of do it, right, you'll see that, you know, you have a truth, and you have a truth, and you have a truth, and then your conclusion is false, right? And so there, right, entailment does not hold, okay, because we found a case where these three were consistent, right? So that's for row 1, and then this was false, right? And that actually ends the investigation right there. Now you may have worked that all the way through, and good for you if you did that, right? But this is something that you can know and you can apply, right? Is if you get to a point where you find, you know, the true premises and the false conclusion, right? Well, then the investigation ends. You can say entailment doesn't hold. Okay, now we're going to determine whether or not this thing is logically true, logically false, logically contingent, right? So this is going to have 3 different atomic formulas. It's going to be 8 rows long, so work on that. Right, you should have got something that looks like that. All right, remember, right, what we have here, you know, is we have, this is the main connective here, this arrow, get my little pointer, okay? And you got to pay attention to that negation again, because that thing is what the consequent is. All right, and then you compare, right, the antecedent, which is a conjunction, those 2 columns there, and you'll get a row of T's in every row. All right, problem 9. Right, I want you to determine whether or not there's a double arrow relation here. Okay, what does that mean? Okay, well, it means whether or not those 2 formulas are equivalent. Right? Determine whether they are equivalent. Okay, so work on that, all right, and come back and talk to me about it, right? Or at least maybe talk to my video, you know, curse at me, whatever you need to do to work out your frustration. And what we'll do then is just kind of talk about this, right, is that we have equivalence. Okay, now what you got to see here is that there's a matching game going on. There's a T here and a T there, an F there and an F there, a T there and a T there and a T there and a T there. So it is equivalent. Okay? All right, last question and then we're done. Okay, we want to figure out whether or not these 2 things are consistent. Now remember, consistency just means that you find a single row where both of them are true. If they're inconsistent, there's no row where they're both true. All right, so work on that. All right, you should get something that looks like this, right? And they are not consistent. Okay, so in each row you inspect, you say, okay, is there a row where they're both true? No. Now we got a T and an F. And then you got an F and a T, F and an F. And that is inconsistency, by the way, right? Even though they agree that they're both false, right, they're not consistent if they're both false. Right, so that's the thing you need to understand. That's why satisfiability might be a little bit better of a term, because what you're wanting is a row where they're both true. And of course the last one isn't like that too, isn't that either, so they're not consistent. All right, so that's the lesson. I know that might have been a little tedious, but I want you to kind of have the basic understanding of how to do these problems, okay? Because when it comes to doing your homework, right, you're going to be given questions that look like that. And if I can just pull it up here and kind of walk through some of those. All right, let's take a look. All right, so if this is homework 5, question 3. Expand this here so you can see that. So you can see that question 3, right, it's just like that. You have to determine whether or not this formula here is logically true, logically false, or contingent. Okay, and so same thing with this question here, right? This one right here is a bit bigger. I'm giving you the space to do this. So, use the space, be neat, right? Be comprehensive, show me your work. I really want you to show me your work. If you just kind of just write in under the main connective, I'm not going to know how you did it, and I'll take points off, all right? Same thing here. This is all just trying to figure out whether or not stuff is logically true, logically false, logically contingent. Okay. Then on question 4, now you're going to be determining whether stuff is consistent or not. All right. So do those problems. Okay. And then for number 5, this is where you got to figure out whether or not whether or not this thing entails this thing, whether they're both equivalent, and whether they're consistent or inconsistent. All right. So you have 2 questions like that. So that's in addition to the front questions that involve things like normal form. All right, and I went over those in the previous lecture. So check that out. All right, and I think that's it. I think that's all I got to say here. I will talk to you later.